Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures on computer architecture. So, we have been looking at pipelining and issues that occur in pipelining and also at increasing performance with the help of pipelining. So, in the previous lecture we looked at techniques more than pipelining, or basically we were looking at how to improve instruction level parallelism. So, we looked at ideas that have been developed such as use of static and multiple issue processors, and we looked at static scheduling and dynamic scheduling. So, we looked at static scheduling in detail. So, in today's lecture we will look at dynamic scheduling. So, again we are talking about multiple issue architectures where there will be the pipeline will be able to handle multiple instructions issued simultaneously. We will look at how dynamic scheduling can be performed in these architectures, some performance issues, and we will conclude with some challenges that occur in these kind of pipelines. We will try to take a look at exceptions in the pipeline. So, coming back to multiple issue, again a quick review of what is static multiple issue and what is dynamic multiple issue. Multiple issue as such is issuing more than one instruction in a given clock cycle. So, in the static multiple issue architectures, the responsibility of grouping the instructions is with the compiler. So, the compiler will group the instructions to be issued together. It will package them into issue slots. So, the compiler is responsible for detecting and avoiding hazards. So, we looked at how the compiler can do this and how it makes use of techniques such as loop unrolling in order to find more instructions which can be executed in parallel. So, this is what we looked at with respect to multiple issue. So, there is one technique, there are other techniques in which are used by the compiler, but that one technique will kind of give you an idea of what the compiler needs to do. So, more about it when you discuss about compilers. So, now coming to dynamic multiple issue. So, what do we expect in dynamic multiple issue architectures? Here the CPU, that is the hardware, will examine the instruction stream and choose the instructions which can issue in a given clock cycle. Of course, you can have some help from the compiler by reordering the instructions, but it is the job of the CPU to resolve hazards at runtime. Okay. So, we will look at some of the techniques that are used by the CPU to do this. Okay. So, when we talk of dynamic multiple issue, we typically use the term superscalar processors. Okay. That is processors which execute more than one instruction in a given clock cycle and where the scheduling is done dynamically. That is, identifying which are the instructions which have to go in a given clock cycle is done by the hardware. So, the CPU will decide whether to issue no instructions in a clock cycle, one instruction in a clock cycle, or two instructions in each clock cycle. And when it decides this, it will take into account that it has to avoid structural and data hazards. So, avoiding structural and data hazards is done by the CPU. The advantage of going for dynamic multiple issue is that you avoid the need for compiler scheduling, though of course as we always say, it will still help. If the compiler schedules it and gives it to the processor, it becomes easier for the processor to do it. So, it can help, but the responsibility of maintaining the code semantics, as we say, that is to make sure that the code executes correctly, is by the CPU. So, that responsibility is with the CPU primarily. So, that is what we look at when we talk of multiple issue, dynamic multiple issue. So, the term that we use is superscalar processors. So, typically we say superscalar processors when we talk of dynamic multiple issue, and we talk of only static multiple issue, we talked about VLIW processors. So, normally we talk about VLIW versus superscalar. So, superscalar is what we are going to look at now. So, let us look at an example again for dynamic pipeline scheduling. So, what we have is a set of instructions, a load, an add, a subtract, and then a shift left. Okay. So, what we want to look at here is we want to allow the CPU to execute instructions out of order to avoid stalls. Okay, that is the basic idea that we are looking at when we talk of dynamic pipeline scheduling. What is it that we have? We have instructions coming in a particular sequence. Now, because of this dependency that you have here, we said that because whenever you have a load and an instruction following that which uses the load, there will be a one clock cycle latency. So, you are losing one clock cycle. So, to avoid that latency, we said that we can put some instruction which is not dependent on this between the load and the add. This is what we did with the help of the compiler. So that is one way of dealing with it. Now what we are saying is, even if this is the order in which it comes, can the CPU dynamically decide that this instruction can go before this instruction? That is, the sub instruction can start, right, while the addu is actually waiting for the value to come from the load. The load word has not yet completed, therefore the addu is waiting for the data to come from there. Meanwhile, if there is one clock cycle that is lost, can the processor go ahead and schedule the sub instruction and execute the sub instruction? Because the sub instruction is independent of these two instructions, so it can actually execute. So dynamically, can the processor pick up the sub instruction and execute it before the add? That is what we mean by dynamic scheduling. So when we say we support dynamic scheduling, we will say that we will allow this order of instructions to be changed during execution. So we call that as out of order execution. The instructions may still be issued in order. What I mean by issued in order is, you will still pick up one instructions in this order. If you do multiple instructions are issued in a clock cycle, that means I will pick up 2 instructions in a given clock cycle. The next clock cycle I may pick up these 2 instructions, but if this is waiting to execute, I will make sure that another instruction which is picked up in a later clock cycle can get executed before the previous one. So we will provide for out of order instruction execution. So if it executes out of order, but what we also have to remember is, how are these values committed to the actual registers, that is the write back to the registers. Can the write back also take place out of order? Now we will see that if you allow that kind of write back to take place out of order, it can result in some hazards. So what we normally do in dynamic pipelines is, you will allow the instruction to take place out of order, but you will commit the results to the registers in order. Okay. So we talk about out of order execution and in order commit. So these are 2 terms that we need to remember with respect to dynamic scheduling. So we will look at how this is typically done in any given architecture. You can see some special structures are required in order to support this kind of a dynamic scheduling, where we will allow for out of order execution and in order commit. So let us look at what kind of structures we will require now in the hardware. So what we do here is, we said that the issue will take place in order, so which essentially will preserve dependencies, okay, because we need to make sure that the dependencies are preserved. So we do in order issue. So since we do in order issue, your instruction fetch and decode will take place in order, okay, that is what we will do. So this will take place in order, but after that the instructions can go to execute in any order, right. So this out of order execution will be done. Now if you do out of order execution, what we also have to do is, the instructions which have been already fetched, if they are waiting for some operands to become available, you have to hold them somewhere, okay. So we use what are called as reservation stations, right. So from the instruction fetch decode unit, the instructions are fetched, decoded, and whatever instructions are waiting for some data to come, they are placed in these reservation stations. So we use these special structures called reservation stations. So the reservation stations are where we hold the pending operands, okay. So this is the purpose of these reservation stations. So we are now, you can see that in order to support this kind of a dynamic scheduling, some additional structures are being introduced, okay. So one major structure here is this reservation station. So the reservation stations typically are attached to the different functional units. So if you have an let us say an integer operation, an integer add that is being that was decoded. So the integer add operation, if it is waiting for some result to come from a load store unit, will wait in the reservation station which is attached to this integer operation. Similarly, if I had a floating point instruction that was scheduled, now that instruction will go and wait in this reservation station which is meant for the floating point unit, okay. So you can look at this as just waiting at some counter, okay. These are different counters which are providing some service. So people will go and wait in these different counters, right. So like that, these instructions come and wait in these reservation stations, okay. Now once the values become available, that is, let us say the load store completes, when the value completes in the load store, right. So the data, that is the outputs that are obtained out of these functional units, will be fed back to the reservation station. So you will have a mechanism to update the reservation stations with the values once they are produced. Once they are produced and they are updated, then these the instructions will go for execution into those into those different functional units, and once that is done, once they complete execution, they will go into what is called as a commit unit. Okay. So, you can take a look at this commit unit. So, you can see that there will be something called a commit unit. Now, this commit unit essentially will consist of some buffers which are called as reorder buffers. Okay. We use the concept, we use a term called reorder buffer. So, why do we call it as a reorder buffer? Because this is the place in which whatever be the order in which they got executed, they are reordered, put in the correct order, so that they will commit correctly in order. That is the instruction which was in the program sequence. In the program sequence, whichever was first, that is the one which will have to commit. Again, remember what we mean by commit. Commit essentially means that you are updating the registers and so on. Okay, that is writing the actual results. Now, meanwhile, while it is waiting in this reorder buffer, that is the completed instructions wait in the reorder buffer before commit. So, you can see that there are two places where instructions will wait. Okay, one is in the reservation station where it waits before it gets executed. Okay, and the other is after execution it will wait in the reorder buffers. Okay, so reorder buffer will consist of completed instructions and their results. Reservation stations will consist of instructions which have not yet gone in for execution, and they will be waiting for the operands to come to them. Okay. So, when the instructions get completed, the completed results along with the instruction information is stored in the reorder buffer, and the completed results are also sent to the corresponding reservation stations which are waiting for them. So, once the instructions in the reservation stations get the data that they are waiting for, they will go for execution. So, you can see that this whole process will just take place automatically. Okay. Now, from the commit unit, okay, so we said we have a mechanism to supply operands for the issued instruction. So, for instance, let us say we had one instruction which was issued, let us say one simple integer operation. So, it was issued, the reservation station was free, the function unit was available, all the data was available, and we had and it has come into the commit stage. Now, there may be another instruction which requires the data which was produced by this. Okay, but there may be an instruction before that which is waiting for something. But because we are doing dynamic scheduling, this later instruction can go for execution by taking the result from this reorder buffer. So, which is why we say that it can supply the operands for the issued instructions. So, you can supply the operands for the issued instructions from this commit stage. This commit stage unit that we are talking about is a huge structure which consists of reorder buffers and mechanisms to supply these operands. Okay, all these things will be provided. Okay. So, you can see that with the help of these major structures and proper data paths which allow data to be forwarded from the commit unit to the reservation station, from the registers, from the commit unit to the registers, and so on, we can have a dynamically scheduled CPU which can be built. Okay. Remember, the two terms that we have introduced here are reservation stations which will hold the instructions before they are executed, reorder buffer where the instruction will be present after it has completed execution. Okay. So, there is information to be provided in this reorder buffer in the and this is the commit unit. From the reorder buffer, it will be committed in order. Okay. So, we say in order commit. So, in order issue, out of order execute, in order commit. These are the three things to remember for dynamic scheduling. Okay. This is how the architecture is built. So, we will take a short break now and then come and continue with the details. Welcome back after the break. So, we are talking about dynamically scheduled CPUs, and we looked at the structure that is required for building these kind of dynamically scheduled mechanisms. So, remember we talked about three things: in order issue, out of order execute, and in order commit. Two structures which facilitate this, one is reservation station and the other is a reorder buffer. Now, the question is, why do this dynamic scheduling? Why do we have to have all this additional structures? Because this requires additional hardware. So, why do I do this? So, the answer for that is that if you were not to do dynamic scheduling and depend only on the compiler to do all the scheduling, so then it could become inefficient. That is, the compiler may not be able to look for all dependencies and schedule code appropriately. Okay. Why is that? That is because not all stalls are predictable. Okay. For example, you could have cache misses that can cause some, that is when you say that a memory is being accessed, you could have a cache miss. So, if you had a cache miss, naturally your load will not complete in time, and therefore another instruction which is waiting for that load will not actually be able to get the result in the next clock cycle. So, which means you will have to wait for a longer amount of time. So, you can't really schedule so the compiler will not know whether a cache miss would occur in a particular instruction or not. So, that is not possible for the compiler to predict and accordingly do the scheduling. Okay. So, this is one important aspect as to why we need dynamic scheduling mechanisms. Another reason is when we are dealing with branches, you can't always schedule around branches. Again, this is because the branch outcome is dynamically determined. So, only when the program gets executed, the instruction gets executed, you will know whether the branch is going to be taken or not taken. So, if the compiler has assumed that it is taken in accordingly scheduled code, but actually the branch is not taken, okay, which is a misprediction by the compiler, then that will lead to some inefficiency. Okay. Same thing is true the other way around. So, branches are something again which require some dynamic scheduling mechanisms. Another reason why we need dynamic scheduling is different implementations of any instruction set architecture, any ISA, can have different latencies and hazards. Same instruction set architecture, same set of instructions, but the way it is implemented in the hardware, it may lead to different latencies and hazards. So, which means the compiler would not know whether the latency was 2 clock cycles here or 3 clock cycles here. If it had assumed 2 clock cycles, but the latency was actually 3 clock cycles and it had scheduled an instruction, it may result in an hazard. So, these are problems that you will have when you are dealing with when you say that only the compiler will have to deal with the scheduling. So, which is why we go in for dynamic scheduling. Okay. So, if you look at today's architectures, most of them have gone through this entire process and many of them use dynamic scheduling mechanisms. But if you look at whether multiple issue and all this talk about dynamic and static scheduling, does it really work? We will find that the answer is that it is successful, but not really as much as we would like. The reason why it is not as much as we would like is that the programs actually have some real dependencies that limit the ILP. Okay. Some dependencies are very hard to eliminate. Example, when we are using pointers. Remember, pointers, what is the actual memory address that it is pointing to, that will not be known unless you actually execute the program, right. The memory address is known only at the time of execution. So, because of this, certain dependencies are very hard to resolve and they are hard to eliminate. So, you may not really get the benefit that we are expecting out of multiple issue. Okay. So, which is why you will see that there are other architectures where we have moved from ILP to thread level parallelism to other types of parallelism. Anyway, so talking about multiple issue again as we said, other difficulties that we have with multiple issue is that some parallelism is hard to expose. So, typically what is happening is when you do dynamic especially, you have a limited window size during instruction issue. When you issue the instruction, you are only picking up two instructions at a time. So, at a given point of time, your hardware only can look at this many number of instructions and say, okay, I now have 8 instructions in my instruction buffer. So, out of these 8 instructions, which are the ones that can execute in parallel? That is all it can do. Okay, it does not have a look at all the instructions which are there and find which are the instructions which can actually go in parallel. That will not be possible for the hardware to do it. That is one problem that you will have. Another is memory delays and limited bandwidth. These are also problems which make it hard to keep the pipelines full. So, though we expect the pipeline to be full most of the time, it may not happen. So, these are some issues that we have to deal with. Okay. Other than this, techniques like speculation and other things have been used. They can help if done well, but again there are certain limitations. Okay. So, this is these are some of the problems that we need to be aware of when we talk of instruction level parallelism, because the moment we talk of ILP and we say we are able to do so much of parallel execution, we need to also understand that there are certain limitations to it. So, that is the point that we need to keep in mind. Okay. Another thing that we need to keep in mind is with respect to power. Now, what is the power efficiency of these kind of dynamically scheduled architectures and so on? All these dynamic scheduling mechanisms, because of their complexity, they require a lot of power. Okay. So, which is why instead of going for highly dynamic scheduled architectures, very complex architectures, we have now started moving towards simpler cores, okay, or multi-core architecture. So, we talk about multiple simpler cores. We say that these can be better than these dynamically scheduled architectures. Okay. So, for instance, to just give you an idea of the kind of developments that have taken place overall from 1989 to say 2005 over here, you can see that the power consumption, okay, if you look at from i486 Pentium and so on, from 5 watts, 10 watts, 29 watts, it's gone all the way up to 103 watts in 2004. And it is around this time that we started looking at identifying that the cores, that a single processor is taking up too much power and we may have to go in for a multiple simpler cores in order to reduce the power consumption. So, you will see that as we move on from 2006 onwards, you will find that we actually move from 2004 to 2006, you can see that number of cores here is 2, right, and the power consumption is 75 watts. Similarly, you can see with respect to UltraSpark, 2003 it is a single core which consumes 90 watts, whereas the same thing, same UltraSpark, but this is a multi-core architecture that consumes 70 watts. So, what we actually see is that though instruction level pipelining has taken us from single issue architectures to multiple issue architectures and so on, if you look at the issue width, that has also been increasing almost from first 1, then 2, 3, 4 and so on. And if you look at out of order execution, whether it is supported or not, earlier architectures are not supported, later architectures it is supported. Okay, and if you look at the pipeline stages also, you will find that pipeline stages have increased significantly. From 5 stages it has gone to 10 stages, 22 stages and so on, and you can see that clock rates also had increased. But again you will see that after 2004, 2005 clock rates actually have been decreasing. Okay, those are some of the trends that you will see. So, overall if you see, though ILP is a very important technique to understand, it is not a solution for all your problems. So, we have other problems such as power which we need to deal with, and which is why we have been now looking at multi-core architectures, where the cores may be simple. You may not have a very complex dynamic scheduling in these cores. The cores may be simple pipelines also, okay, but we need to understand that both these extremes are possible. Now, this is just an example of Opteron X4 microarchitecture. So, this will tell you how an Opteron processor actually looks like. Okay. Basically, you can see that it is a complex architecture which we talked about, right, which has dynamic scheduling. So, you will find that this has all the different structures that we talked about. Okay, that is something that we have here. So, other challenges, coming back to our pipelining, let us look at a few other challenges before we conclude on pipelining. The important things to remember with respect to pipelining is that if it is a poor ISA design, it can make pipelining hard to implement. So, we can see that complex instruction sets is difficult to implement pipelining, which is why we will see that the moment we talk of pipelining, we make use of simpler instruction sets. And again, complex addressing modes are challenges to pipelining, delayed branches are challenges to pipelining. Another challenge that we need to understand with respect to pipeline is what we refer to as exceptions and interrupts. Now, so far we have not talked about something called interrupts or exceptions, though these are some things which will always occur in your program when your program is getting executed. Of course, we will look at more on interrupts when we talk about input output devices and so on, but from the point of view of pipelining, we need to understand a little bit about exceptions. Okay. So, what is an exception? Okay. An exception, you can say, is just some unexpected event which requires a change in the flow of control. Okay. Different ISAs use the term differently, but this is what we will look at. So, some unexpected events. So, it may be an exception which arises within the CPU. So, typically we use the term exception versus interrupt. Exception normally is something which arises within the CPU, some event that has actually happened within the CPU, but requires some change of control. Okay. So, this could happen because of, say, some undefined opcode was encountered, so which means you can't execute that instruction, or you may have an overflow that occurs. When an operation occurs and an overflow takes place, you may want to treat that as an exception and take some specific measure based on that. Okay, or a system call is made. All these are referred to as exceptions which may arise within the CPU. On the other hand, you could have interrupts which are caused by some external event, some external IO controller, say your keyboard controller, your mouse operation. All these things, when you press a key on the keyboard, will lead to an interrupt because that needs to be processed. So, these have to be dealt with. Now, the problem that we have in dealing with these, especially with respect to a pipeline, is that in your pipeline you have multiple instructions which are being executed. Now, if an exception occurs or an interrupt occurs, what do? Okay, we have to stop the pipeline, right? We have to stop that execution, bring in a new set of instructions that need to be executed because a new control has to be brought in, and we have to take care of this exception or the interrupt and then come back and resume your operation. Okay. So, now we are talking about pipeline being executed, something happens, so I have to stop the pipeline, okay, flush everything out of the pipeline, I have to remove things from the pipeline, right, I have to remove things from the pipeline, bring in a new set of instructions into the pipeline, execute that. When that gets completed, bring back the original pipeline, whatever was there in the original pipeline, and then continue execution. So you can see that the implementation of the pipeline, especially if the pipeline is very deep, all these things can cause a lot of problems to this. Okay. So we will just look at what we normally do when we handle these kind of exceptions. So what is normally done is, whenever an exception occurs, so what is done is, the PC of the offending or the interrupted instruction, that is saved. Okay, you save the PC of the instruction. Why do I save the program counter? So that from that instruction onwards you can start loading the instruction again when you want to resume. Okay, so first you have to save the PC, okay, and you save an indication of the problem. What is it that caused the problem? You have to save that also. Okay, and then you have to jump to the handler. What is the handler? Handler is the one that is going to handle that exception, that is going to take care of that exception. So an exception handler or an interrupt handler we refer to. So you will have to jump to the handler, which will be at some specific location. Now how will I know this specific location? It may be some standard location that is used, or an alternate mechanism is what is called as a vectored interrupt. In this case, you will determine the address based on the cause. Okay, that is, you can say an undefined opcode, the handler address is this C00020. If it is an overflow, the handler opcode, the handler address is C0000020. If it is some other this thing, it is at some other address. So depending on the type of exception that I have got, I can find out where the handler is located and load the instruction from this location, and then you can start executing. So this is another mechanism that you can use. What will the handler typically do? What is it that you are expecting this handler to do? It will first read the cause of the event and it will transfer to the relevant handler. It will determine what action is to be required. If it is restartable, then you will take the corrective action and then it will use the EPC where you had already stored the original PC, right? You will use that to return to the program. Otherwise, you will terminate the program. Okay. What do I mean by restartable? Some interrupts and some exceptions, when they occur, you do not want to terminate your program. You want to continue with the execution. So if it is so you always have to determine whether it is a restartable type of an exception or a terminate type of an exception. So if it is a restart type of an exception, then we will restart execution. Okay. So to do the restart is why we have to store the original PC in some location, which is normally stored in some special registers, and then we will have to restart execution from this stage. Okay. So these are additional things that we will have to handle when we deal with exceptions and interrupts. Okay, and these make pipelining even more complex. Okay. So to summarize, what we have looked at today is dynamic instruction issue, dynamic scheduling of instructions when we are dealing with multiple instructions being issued per clock cycle. So we looked at the structures that are used for this dynamic scheduling mechanism. So we looked at some challenges that are there when we are dealing with pipelines, and another aspect that we looked at is exceptions. What is an exception and why we need to worry about exceptions, especially when you are dealing with a pipeline. Okay. So this is what we have looked at today. So questions to review today's content. Question number 1, what is meant by dynamic scheduling? Question number 2, what is meant by out of order execution and in order commit? Question number 3, why are these necessary for correct execution? Question number 4, what is an exception? Question number 5, how does an exception affect a pipeline? Thank you.